supposed to have known from your reading guide 8. So let's write those out before we move on. What were the 7 diatomic molecules? H2, right? Hydrogen, nitrogen. Let me write this in a different manner so you remember it. So hydrogen, keep going. Nitrogen, keep going. Oxygen, fluorine, I'm almost iodine, bromine, and then iodine. So these are the 7 diatomic molecules, and you should know that are considered diatomic. You can see that I've written them on their little lonesome self with a min and e next to it, so with a 2 next to it, meaning I have 2 fluorines, 2 chlorines, 2 bromines, and 2 iodines for each of them. And the way you remember it, there are 7 of them, right? 7 of them. It's the big 7 in hydrogen. And that's exactly how they look on the periodic table if you look at it closely. The big 7, starting at the nitrogen over here on the periodic table, NOFClBri, that's a big 7, right? Basically, and then hydrogen over here. So the big 7 in hydrogen are the diatomic molecules. And instead of saying diatomic atoms, they're not atoms, right? They're molecules because they're combined together with another nonmetal, meaning they're covalent compounds. Water, additionally, so H2O, that's a molecule of water, not an atom of water. Because what do atoms, what does that term refer to? Simply elements, right? So give me an example of an atom. An atom of iron, an atom of silver, an atom of cobalt, an atom of any straight element from the periodic table is what we would refer to as an atom. So give me an example of a formula unit. Don't say sodium chloride. You had about like 5 or 10 of them on your quiz. Say again? Barium chloride would be a good example of a formula unit. What else? Copper what chloride? Okay, so copper 1 chloride like that, or copper 2 chloride like this. Okay, so you can keep going on and on. Anything ionic we could call a formula unit. Okay, so those are called representative elements, or representative particles. And those, they come in 3 varieties, like 3 different flavors. So let's go back here. This actually, I think I've given you a little bit of this on the back of your note sheet from yesterday. On the back of your acid sheet. Thanks, Harvey. Back of your acid sheet. Let's see here. Not quite here, but it's coming soon. We're going to be moving to this in just a couple minutes. So the mole, first off, we know it's an SI unit, and this was in your reading guide 10. So that's it. This is why I left reading guide 10 on your desk. So you could star things or highlight things in your reading guide because you've already written it, so now you're seeing it a second time. Make sure you're denoting that's important information. We know that the mole is also equal to 6.022 times 10 to the 23 particles, and that number is named after a man called Avogadro. Yes, ma'am.
Where is this?
This information is not there yet, so we're getting there soon. Okay? So the definition will always allow for us to convert between what and what. So the conversion between the mole, so between moles, and something else. So what are we relating the mole to in this first example? Not mass yet. What's in this example? Okay, formula units, so that's just one example of it. Representative particles, okay? So definition mole always allows us to convert between moles and number of particles. And the particles, that's not very, very descriptive, right? Particles come in 3 flavors, and that's what I have here. Particles can be referred to as what, and what? Atoms, right? Molecules, or formula units. So particles is a generic word, like you guys are people, right? You're all people, it's a generic term, but I could say sophomores and juniors, or I can go girls and guys. I can go tall and short. I can be a lot more descriptive than just people, just like I can be a lot more descriptive than just particles. Okay, so that's going to be one conversion that we're going to be talking about, and that's what you guys just wrote information down about. Okay, next one, and that's where we have the mass. Come right back to that. So all of this up here, I'm going to skip this blurb of information for a second. We actually have this definition back from Unit 1. We know what atomic mass is. If you had to find the atomic mass of something on the periodic table, you probably could. So tell me the atomic mass of potassium. Is potassium on the periodic table? What is its atomic mass? 39 point. Okay, so about 39.1-ish, right? Well, that atomic mass is referring to 1 mole of potassium. So what's the mass of 1 mole of carbon? 12.01. Making sure you're looking at your tables, you know what we're talking about. What's the mass of 1 mole of sulfur? 32.06. Okay, so this information on the periodic table is telling you 1 mole's mass. So the mass of 1 mole of any compound, or we call it also its molar mass, which we have referred to before. The mass of any 1 mole of a compound is the molar mass. It is numerically equivalent to the atomic mass in the periodic table. So these two things basically are equivalent. And this is where I think your notes start on your paper, yes? Yes? Okay, cool. So the mass of 1 mole of sulfur is, you just told me this, 32.06 grams. Okay, so 1 mole of sulfur is equal to 32.6 grams, and that's straight from the periodic table. All right, so iron. What's the mass of iron? 1 mole of iron. Okay, so 55.85 approximately, right? Okay, so that number is actually right here, 55.8 grams of iron. You told me that this is equal to 1 mole, because 1 mole of iron is what the periodic table's mass is. So how many atoms would be in that mass? I heard it. Number of atoms. I started to hear it. Loud and proud? Okay, well, I'm going to say it as the mole is written 6.022 times 10 to the 23rd. So how do we know that? 6.022 or 2 times 10 to the 23rd atoms. How do we know that many atoms are in 55.8 grams? Because that's 1 mole. So there's 3 things being equivalent here. 1 mole of iron equals 6.022 times 10 to the 23rd atoms of iron, which also equals 55.8 grams of iron. Those 3 things are equivalent. So the mole is, remember, we're relating it to 3 separate things, just like we had 3 separate things here. We're just learning how they relate across the board together. Okay, so lastly, if I wanted 6.02 times 10 to the 23rd atoms of carbon, what mass of carbon would I need? You shouldn't be looking at me. Where should you be looking? 12.01, where are you seeing that information? Periodic table of elements, okay? So that's because 12.01 grams of carbon is equal to how many moles of carbon? Say again? 1 mole of carbon. And that's because you know that the carbon mass in the periodic table is equal to 1 mole of carbon. And so since these 2 things are equivalent, they're also equal to the number of atoms that are in a mole. So we're relating these 3 things back and forth with each other. So before I move on, let's go ahead and do a bit more complex calculation of molar mass. Literally adding things together, and that's it. Don't just get too crafty on me, okay? So whenever I look at molar mass, sometimes I have just an element, so like carbon. Sometimes I have a full-on compound. So let's go ahead and calculate the molar mass of C2H6. Yes?
How far would you want to go in decimal place wise in that?
So generally, most of our periodic tables have 2 decimals for masses. Most of them do. I think your pink one might be a little bit more accurate. So that's 3. So if your periodic table that you're using religiously goes to 3, then go to 3. If it goes to 2, goes to 2. I have a lot of these memorized to 2, so I'm going to go. Probably most of my answer keys will be to 2, just because I've used it like that for longer. So what you're doing here is there's 2 carbons. So you're saying 2 times what? 12.01 grams, okay, plus 6 times hydrogen's mass, which is 1.008. Okay, so 2 times 12.01 is 24.02, plus that is 30.608. Yes, okay. And here's how you write the units. Do not let yourself slack on this. Grams per 1 mole. So the molar mass has 2 units, moles and mass. Molar mass has 2 units, moles and mass, right? But we always say it grams per mole. We don't put moles per gram. Alright, so you should be actively calculating with me because I can see the sleepiness setting in. But work with me, okay? So we've calculated the molar mass of 180. How would I change, how would I actually find the molar mass of this guy? How many of each of the atoms do I have? Yes?
Because we're in the question. Molar mass of C through H6 is 1 mole. Would that be equal to the mass of iron 8 grams since they're both equal 1 mole?
No, and that's the special part. I'm really glad you said that. So it's not a stupid question, it's a good question. Bananas, 12 bananas. They're gonna weigh 3 pounds. But if I had 12 grapes, how much do you think they would weigh? More or less? Less. Okay, so different elements, just like different fruits, have different masses. Meaning if I got a mole of bananas, it's gonna weigh a ton more than a mole of grapes. Just like this example. A mole of C2H6 weighs 30-ish grams per mole, but a mole of iron weighed what? 55.8. That just simply means iron is just naturally heavier. It's more dense. It weighs more. So that's actually a really good point. They are not equivalent whatsoever. They both equal a mole, but their masses are different. Cool. Good question. Glad we could clarify that. Okay, this one. How would you find its molar mass? Another question? Okay.
Why is it that, like, if there are 12.01 grams in a mole of carbon, why is it that there's several moles of each element in a compound? Like, how's that still the same?
Because a mole is a number in a compound. So, like, for example, we sometimes call things internal mole ratios. I think I'm going to clarify that in a minute, Jillian. So hold on a second. You guys have to put the molar mass of magnesium actually. Now, alright, so I'm actively calculating molar mass of magnesium nitrate. Yeah. Alright, so Praneeth's going to guide us here. So Praneeth, tell me your process. No, just guide us. Tell me your process.
I think first you have to distribute the two
To each or to who? Give me
to
specifics.
each element within the parentheses.
Within the parentheses. So this 2 does get distributed to nitrogen and 3 oxygens, right? So let's do this step by step. What's the molar mass of, what's the mass of magnesium? Okay, so 24.31 is what I have memorized, so I'm just going to go with that.
Yeah.
That's good. And then how many nitrogens do we have? 2, so 2 times N, so that's 2 N's, and that's 2 times 14.00, where am I getting that? Nitrogen, right? Okay. How many oxygens here? 6, so 3 times 2 is 6 oxygens, so 6 times oxygen is 16.00 for oxygen? Yeah, okay. So add all those up. Boom, boom, boom. What do you get? 248 what? Ooh, 148, sorry. 148.25. Thanks, Darcy. Guys, I need somebody other than Darcy to calculate for me, because this is where your muscle memory comes into action in a week or so when we have this test. 25 what? 9 grams per mole. Yes, ma'am. Carolyn.
How exactly did you get to 9?
I'm listening to Darcy on that one. So as long as we're close to this, guys, as long as we are close to this, we know how to add. But really, that part about distributing was what we need to model for you guys here. Yes. Oh, well, you're multiplying the 2 times the 14. No, not by each other, right. Molar mass is a summative mass. Summative mass, that's another good point. Okay, so far, we've gone over 2 parts of this. We've gone over the mole's relationship to number of things, meaning atoms, molecules, and formula units. The mole's relationship to just a mass of a certain compound or a certain element. What's the last one we need to do? The molar volume, right. So I think, Julian, I'm going to answer your question here in a second or two. So molar volume has a relationship. It has its own number. It's going to be 22.4 liters per mole. And this is actually only for a gas. at a specific condition. So the specific conditions are called STP, standard temperature and pressure. Can someone circle that or look on your reading guide 10, so star by that, because that's something you're going to want to study. I try to sometimes leave you the reading guides in front of you so you can see that you've already written down some information about this. So on your reading guide 10, you wrote down standard temperature to be what? Say again? 0 degrees Celsius. So 0 degrees Celsius, remember, how do we get from Celsius to Kelvin? Add 273, right? So add 273, and what do you get for Kelvin? 273 Kelvin, and that's what I have right here. Okay? And then you also wrote down something else for your pressure on reading guide 10. What was your pressure for reading guide 10? Lindsay. 101.3 kilopascals, 101.3 kPa, kilopascals. So guess what that's equivalent to? 1 atmosphere. ATM is atmosphere, not atoms. So another thing that people think is briefly. 1 atmosphere. And so we live at approximately sea level here in Charlotte area. And so that approximately gives us an altitude of 0, and that approximately gives us an atmospheric pressure above us of 1 atmosphere. But if I live under the ocean, do you think the pressure is greater or lesser under the ocean? A lot greater. It's probably like 2 or 3 or 4 atmospheres of pressure, a lot more pressure. If I live on top of Mount Everest, what do you think the pressure would be? A lot less, because I'm up in the sky, there's less pressure, there's less air pushing down on me. So the pressure is like 0.5 atmospheres. It does differ, but this is very, very specific. You can convert between moles of a gas to volume of a gas by using 1 mole is equal to 22.4 liters, that conversion factor, only when you have STP conditions, 1 atmosphere and 273 Kelvin. Yes, ma'am?
How do you get to STP conditions?
We are going to work with gases a lot more later, but really, we will assume a lot right now, and we are going to assume we are always at STP conditions for this point in time. Yes?
I understand the math for like the numbers we're doing, but I don't really understand like what a mole is.
So that's the thing, that's the hardest part. A mole is just a bunch of stuff. 6.22 times 1023 items. And those items, those things, can have a specific mass and a specific volume. Just like a dozen bananas can have a specific number of them, a specific mass of them, and a specific volume of them, which is a big, huge number of things. And they have a mass associated with them and a volume associated with them.
So it's just like another way to like characterize something?
Yes, another way to describe it. Yes, yes.
Kilojoules, it was energy. Does this have like a certain thing?
So this has 3 things to it. Its mass, its volume, and its number of things. They all can be related to each other. So basically means I can convert from things to moles, from mass to moles, or from volume to moles. Never will I convert from volume to mass or volume to numbers, because those don't have any connections between them. You have to go from your volume back to mole, then to number, or banana back to mole, then to number. So that's what we're going to do next. We're going to learn how to convert between them and relate them to each other. So here we go. I'm going to give this some application here. It's 8 o'clock. I'd like to practice for about 15 minutes with you guys, and then I can set you free to work some within your groups. So what we're doing now is we're putting these 3 relationships into complex relationships. So we have a question. I want to model to you how to do a couple of these first. You guys have these questions on your paper. Make sure you're following along with me. First, I want to think about the relationships, and then we're going to apply it. This question gives me a number of atoms of silicon, so just a number of atoms. And it's telling me to convert it to moles. Is there a direct relationship between atoms and moles? Yes. I'm going to rewrite these about bananas. I'm going to write these as what we just talked about. This is on your paper, so mole can be related to number of particles, to molar mass, and to molar volume. You need quickly what the relationship is between each of these. If I'm going from mole, and you guys, let me go ahead and go back. I'm going to add it on here because you guys might actually want to add that to your chart. This chart here, okay? So write this for me now. What's the relationship between mole and number of particles? What's that number, that conversion between them? 2 times 10 to the 23rd. And that's number of particles in 1 mole. Yes,
We have to put 6.022 just
either one will work. Either one. It's not too different. Okay, what's the relationship between moles and molar mass? Where would I get the molar mass from? Right, and that's it. Say it again. Okay, so atomic mass from the PCOE, periodic table. And I don't have a specific number for that because that's what Nick said earlier. There's a different number for every single compound. This one has a specific number. This one's going to be variable based on the compounds of interest. And then lastly, what's the relationship between mole and molar volume? There is one number for this. Yeah. 22.4 liters per 1 mole. Okay, so that's what we're going to be utilizing, those relationships throughout this process. Okay, so first question relating atoms to moles. What is the relationship between atoms and moles? So Avogadro's number, 6.022 times 10 to the 23rd. So what we're going to do is we're going to start with our given. The given here is atoms. Rewrite that here as 2.80 times 10 to the 24th atoms of Si, silicon. And we're identifying the unit and who it's describing. And we are doing dimensional analysis again, okay? So this is back to unit 1. Don't give me that sad face. This is going to be better than the last time, because now we're applying it to more chemical reactions-based things. So now we have atoms. I want to convert 2 moles, right? I want to convert 2 moles. Do I want to put moles on top or the bottom of this next fraction? On top. So 1 mole of silicon has how many atoms in it? I hear you. 6.102 times 10 to the 23rd atoms of silicon. Okay, have will our atoms cancel? Are there atoms on top and bottom of a fraction? Yes. Atoms of silicon cancel. Atoms of silicon cancel. Pull out that calculator. I want to see you calculating because I know you sometimes don't put your parentheses and it causes issues in calculation. So what you would be putting in your calculator is parentheses. 2.80 times 10 to the 24th. Parentheses. Divided by. Parentheses. 6.102 times 10 to the 23rd. Parentheses. And Emily, you got that? Yeah.
4.65.
So 4.6511 times 10 to the, oops, sorry, no times 10 to the, that's it, right? What are the units here? Units that are remaining? Moles of silicon. Okay. So I'm going to look at sig figs now. So sig figs are, based on the first number, how many sig figs are in this first number? 3. And then if we had 3 or 4 here, either way, 3 would win. So then how many numbers should this be rounded to? Or what should this be rounded to? 4.65 moles. 4.65 moles is the answer, guys. MOL is an abbreviation for MOLE. Ooh, one letter drop, right? But MOL is mole. And that's it. We converted because we knew the relationship between moles and number of particles. Let's do the next one. We are starting off with our given. Given here is 0.32 moles of potassium. What is potassium's symbol? K. All right, so we're starting there. Now your next thought is, do I have a direct relationship between moles and grams? Yes. And what is that called? Molar mass. Okay. Jacob, what's the molar mass of potassium?
Is 39.10.
Okay, do I put it on top or bottom of this fraction if that's the mass?
Bottom.
So close. So hold on, before I move on, let me actually fill out the rest of this before I ask for that again. So the relationship between this is 1 mole, and I'm not putting this in my fraction, I'm just writing this to the side for you. 1 mole of potassium is equal to 39.10 grams of potassium, because that's from the periodic table. So this is my conversion factor. Do I put that with the mole on the top or the mole on the bottom to cancel moles out? So this 1 mole of potassium, that's going to bottom because I have to cancel moles out. So 1 mole of potassium weighs 39.10. And thank you. That's what the mass is. And that mass has to go on top so that I can cancel out moles and moles, leaving me with mass, because my question was mass was grams. And that's grams of potassium. So this is the conversion factor. This is the equivalency. And that's what I put right here in my fraction. So in your calculator, you're doing 0.32 times 39.10. Your moles of potassium have canceled. What's your answer, Robbie? Calculator out. Thank you. Someone else. Rishi. 12.51. Yeah? Okay. And how many sig figs should I have here? 2. So what should I round to? Right. So 12.5. The 5 rounds a 2 up. So that's 13 grams of potassium. 13 grams of potassium is your answer. Okay. So far, so good. We've gone from moles to atoms using Avogadro's number. We've used moles to mass using molar mass. Let's go to, I'm going to go to 5. Ooh, yeah, actually, no, I lied. We'll come back to that one. Let's keep going easier. All right, so now we have some specific stuff happening. We've got atoms involved and moles involved, but realize that the moles of SO3 is what I'm starting off with, but I'm not ending in atoms of SO3. SO3, is that a molecule or a formula unit? So SO3, is that ionic or covalent? That is covalent, right? If it's covalent, do I call those molecules or formula units or atoms? Molecules. So these are talking about molecules. So now we have a problem, because that's asking for atoms of oxygen, so that's not apples to apples. We're changing the thing we're talking about as units in the problem. So let's just kind of get started, and then we'll kind of figure out our way as we go. Start off with your first number, 1.14 moles of SO3. Now, noticing that I'm going all the way down to just teeny tiny atoms of oxygen. Before I get down to atoms of oxygen, I need to get to molecules. And here's kind of what you're thinking. I'll write this over here, actually. SO3 kind of looks like this. And I'm not doing it to, well, I'll do it here. This is basically what it looks like in the Lewis-Dot model. That's what it looks like, right? In that one molecule of SO3, how many atoms of oxygen are in it? 3. You just made your own conversion factor. Yay, you, okay? So this is good. This is what you need to do for yourself occasionally. And I'm going to write this down here. One molecule of SO3 contains 3 atoms of oxygen. And since this is true, this is a true statement, this is an equivalency, we can use this as a conversion factor later on. And I will tell you, it's going to be the very last thing to use, because we see 3 atoms here of oxygen. The question's asking for atoms of oxygen. That has to be my last step, right? Do you see why? Because the atoms of oxygen are here. So before I get to this as my last step, you can see I had molecules of SO3. That must mean I had to have had molecules of SO3. So how do I get from moles to molecules of SO3? 3 relationships. Which one? I have to use Avogadro's number, because that's going to number of molecules, numbers of things. So here we go. Let's go ahead and do that next. We have 1.14 moles of SO3, and you say I'm going to use Avogadro's number. Do I want to put moles on the top or moles on the bottom? Bottom. So remember, you're always referring to 1 mole, and that 1 mole of SO3 has how many molecules in it? 2 times 10 to the, times 10 to the 23 molecules of SO3. Yes, it's important to write the identities, because as we change identities, SO3 to oxygen, I won't know what you're talking about, nor will you. So now our moles of SO3 cancel, moles of SO3 cancel. Now I have molecules of SO3. How do I get from molecules of SO3 to just simply the atoms within it? Yes.
How exactly did you get that?
How did I get here? Yes. I realized that I was going from moles to molecules, and the molecules is a specific particle, and the particle relationship is Avogadro's number. So that's denoting this relationship right here.
So you're multiplying that by that.
Yes, I'm just not going to do it in my calculator just yet. Okay, so now I've got molecules of SO3. You guys know that I want to cancel out molecules of SO3, because who wants that on the top anymore? Nobody. So here's the next step. We already have it. We just have to put it in action. I have 1 molecule of SO3 equaling 3 atoms. So I'm going to put the 1 molecule in bottom of SO3, and it has how many atoms of oxygen? 3 atoms of oxygen. Oops. Oxygen, just straight up O. And am I done with getting to my final unit of interest? Yes. My question was atoms of oxygen. I'm to atoms of oxygen. Now all I have to do is math. Calculate. 1 second. Before we move on, go ahead and calculate for me first. And Caroline, what's your question, honey?
I'm just saying what we do now.
Now you are going to calculate. So across the board, we should have moles of SO3 canceled, molecules of SO3 canceled. The only unit that we have remaining is atoms of oxygen, and that's what our question was. So we're in a good place.
We have to multiply 3 by whatever we got from the
On the top, right. And anybody have that for me? I'm gonna stop there, okay. Times 10 to the 24th atoms of oxygen, right? Okay, so anybody else get this? Okay, we're looking good. How many sig figs should I have? 3, because this one has 3 sig figs here. This is not a measurement. It's just counting a number, so it's not truly a measurement. So we're gonna say with those 3 sig figs. So there should be, what should the final answer be here? 2.06 times 10 to the 24th. Don't cut that off. Atoms of oxygen. Okay. 2.06 times 10 to the 24th atoms of oxygen. Yes.
I'm confused on why you got rid of sulfur.
So that's where I drew that picture, and I made this decision that in that picture of SO3, I said one molecule of SO3 had 3 atoms of oxygen in it. So that's an equivalency. That equivalency is not truly, they're not equal to each other, because like, how do you say 1 mole of SO3 is equal to 3 atoms of oxygen? Like, that's compared to different things. But it's the idea that in 1 mole of SO3 there are 3 atoms of oxygen. So it's kind of like an agreed upon assumption that we're making. Yeah.
Is there any calculations? Is there anything like times 10? Can I just take the E?
I think you can, but I prefer the times 10. That way you don't accidentally write E on your paper, because E is like nothing. Just don't put E on your paper. Okay. Okay. So let's keep going. I'm gonna give you guys a shot at this one. Do number 4. Talk in your groups. I'm trying to go slow, but I'm trying to go too slow.
Well, if you do how many grams is in 1 mole? You can't go straight to the grams. So we have to figure out what the version
I think you're making progress. I just want to give a quick check right here. So back to me in 5, 4, 3, 2, 1. All right, so at the very, very top of this, I said there's this process that I'm going to try to enforce. And this is how I learned chemistry, and I found success in it. Obviously, I'm doing it now, right? So always identifying your unknown, identifying your given. So I went ahead and just modeled that here for you. So it helps get rid of the distracting questions. So like you can imagine this question is maybe in a word question where you have lots and lots of sentences and details, but really the important part is I know I have been given the moles of sodium phosphate. Who got sodium phosphate's formula right? Give me a thumbs up. Okay, use your polyatomic ions for now until you get used to them, because I don't want you to mistakenly have the wrong formula. The question is getting to grams of that. So this is where it's really easy for you, because your job now, you have one job is to figure out how do I convert. Is there a direct conversion between moles of this thing and grams of that same thing? Yes or no? There is a direct conversion, and what is that called? Molar mass, right? It's that mole to mass conversion. So where would you then be finding the molar mass? The periodic table. Look at the compound, find the periodic table, match up the symbols, make sure you're distributing if there's a necessity for that. But in this case, there are 3 sodiums, 1 phosphorus, and 4 oxygens. What is its molar mass? I heard 3 different things. 163.94. Do I have to put on the top of the fraction or the bottom of the fraction? Top. 163.94-ish. Yours might be a little different based on your periodic table. Grams of sodium phosphate. Now that number is equivalent to how many moles? 1 mole, right? Remember, it's always 1 mole. Don't get crazy on me. Remember this number over here for mole. One of those is equivalent to each of these things. So 1 mole of sodium phosphate. What happens to the units of moles then? They cancel here, they cancel here. Wonderful. What unit is the only thing remaining? Grams of sodium phosphate. And then you guys can tell me what that is based on multiplication. Jillian, do you have that? Jillian, do you have that? Yeah. 0.741 grams of sodium phosphate. I'm guessing that you rounded to 6/6. Wonderful. All right, give me a thumbs up if that one made sense. This was easier than the last one. Last one we did some dissecting. We were like, here's SO3. We're looking at just the oxygens. This was apples to apples. We were comparing the same thing. Now we're back to another one that we're dissecting with. Let's talk to the process first. What is your given? What unit is given to you? We're given liters of, what is carbon dioxide? CO2. That is our given, liters of CO2. What is our question? Atoms of what? Now we have atoms of oxygen, just straight O. That's our question. Noticing we're going from CO2, just plain old oxygen. So we're going to have to kind of figure this out before we really, really get started. So what would you be comfortable doing first? If we have liters, what would be an easy conversion for us? Convert it to moles. So this is your guideline, this is your roadmap, right? You have liters, you're here in volume. You only have one connection, one, and it's to mole. There's no conversion between volume and mass or volume and number. It's volume and moles. So let's go ahead and do that first, and let's talk. So let's go ahead and take our 2.5 times 10 to the 2 liters of CO2 and convert that to moles. Where do I put mole? Top. 1 mole of CO2 contains how many liters? Where are you getting the number from? From your paper or from your head, right? 22.4 liters is what that conversion was required to be. Okay, so that only does us one favor, and it gets rid of liters. I'm not even going to calculate yet. It gets rid of liters and liters. Okay, so now I have moles of CO2. Moles of CO2 doesn't necessarily relate to atoms of oxygen, but I could, if I'm in the mole here, I'm here, I could go where next? Say again? I got to the number. Now, if I'm going from mole to number, what's the appropriate term to describe CO2? An atom, a formula unit, or a molecule? Why molecule? It's covalent. Okay, so we're going to go to molecules next. Awesome. You guys are getting it. You're connecting the dots here. So I have 1 mole of CO2. Where do I put it? On the bottom, so moles can cancel, right? Moles of CO2. And a single mole of CO2 has how many molecules in it? 6.02 times 10 to the 23rd. So a big number of molecules of CO2. Okay, guys, we've gone from a humongous number of CO2 molecules. Now hone in on one CO2 molecule. Hone in. Think about it. What does it look like in a Lewis dot model? Or just think about it and draw it out for yourself. What does CO2 look like? Who's in the, and you know it's covalent, so you know who's in the center. The carbon's in the center, and then what? 2 oxygens, right? Okay, I don't even care if it's completely drawn. Don't even draw it for yourself unless you want to. But what you should notice is in one of these, and I'll actually draw it right because I'm, I'm a teacher. Okay, there you go. So CO2 looks like this. In one of these molecules, how many oxygens are there? 2. And you don't have to draw it to know that, right? You could totally just look at the formula. CO2, there are 2 oxygens inside of 1 carbon dioxide. Does that make sense? Yay or nay? Give me something. You're making your own equivalency here. You're saying, I have 1 molecule of CO2. It has 2 atoms of oxygen in it. So here's what we just said out loud. I have 1 molecule of CO2. And it has how many atoms in it? 2, how many atoms of oxygen? 2 atoms of oxygen in it. And we came up with this by logic. Do you think you can continue to do that based on your drawings and your understanding of what molecule and atoms mean? That's your job there, okay? So, here we go. Our liters of carbon dioxide canceled. We then said we had moles. And I can't go atoms yet. I got to go to molecules because that's a molecule of CO2. So you cancel your moles of CO2. Then you have your single molecule of CO2. And you then made that equivalency to atoms. Are we to our final destination? Are we to our question? Yes, because we got 2 atoms of O2. And that's the only unit left. So let's calculate across the board. Use your parentheses as needed. I'm going to get to this last one in a second, and then I think we'll be okay. So you're doing 2.5 times 10 a second. Divided by 22.4. Times parentheses 6.02 times 10 to the 23rd times 2. Anybody? Rishi.
1.6.
Times 10 to the 25th. And what are those units here? What are the units? Atoms of oxygen are the only units remaining, right? So atoms of oxygen that we get here. Okay. And 2, how many sig figs should be here? 2 sig figs, so what should I do with this number? This should be 1.3 times 10 to the 25th atoms of oxygen. Our board keeps cutting on and off, so you deal with it, yeah. I could ask you for atoms, something from a formula unit, which is the same thing as an ion compound. You could still just count up your ions of that. Same story, just different idea. Okay, let's do this last one together. You guys get started. I have about 5 minutes left, so let's go ahead and knock this baby out. I really hope you're writing down all your sample examples because you're going to want to refer to these on your own later. You got the formula for lead 2 iodide. PBI2. Alright, nomenclature is here to stay, so make sure that you ask me questions on those as needed. I think maybe you had enough time to look for your question. Your given, which was your formula unit. That formula unit, that word. Which of these on the board is it describing? Is it describing number, mass, or volume? It's describing number. So molecules, formula units, or atoms would indicate to you that you're talking about the number. So there's only one step you could really start with, right? What do you have to do with those formula units? Convert them to what? There's only one connection here, right? I'm just going to keep going up here on the board again. Formula units to moles is the only relationship you have right now, so you have to use that. So what do I write here? What do I write on top? Say again? So is the 6.022 times 1023, is that referring to the formula unit number or the mole number? The formula unit number, right? That's the number of things. So do I put that number on the top or bottom? Put it on the bottom, because the formula unit has to get canceled, right? So the formula unit is the thing canceled. So its number is 6.02 times 10 to the 23rd formula units of PBI2. And that's equivalent to how many moles? 1 mole of PBI2. And that's why the mole goes on top, because the formula units have to cancel. So I'm here and I'm canceling. Oops. So as I'm canceling here, now your job is to figure out, look at our final unit of interest, which is, you can see mass, which is grams of PBI2. I'm right here now. I've gone from formula units to moles. How do I get to mass? Say again? Due to mole to mass relationship, right? Mole to mass, molar mass is going to be the molar mass of PBI2. So then where are you pulling that information from? Periodic table. So do I put mole on the bottom or mass on the bottom here? Right, 1 mole of PBI2 weighs 461.008, and that's like 207 from lead plus 126.7 from 2 iodines, so that's times 2. So that's a big number, and that's okay, of PBI2. So from that information, we went from formula units using Avogadro numbers to moles, and from moles using the molar mass to mass. Are we done? Yes. You got a calculation for me? Calculation 20.46. 1.46 grams of lead 2 iodide. Yeah, that looks pretty good. Yeah. Okay, you guys have 8 questions. The 8 questions are right in front of you still. They're on your paper. And I want you to circle them so you remember that is what I want you to do. I say start problem set 10 or continue. What I want you to do really is to focus on from your sheet. Student practice 1 through 8. Use your polyatomic ions to help you with the nomenclature section so that you're successful with the new part, the molar mass and the volume and the molecules. But you guys are responsible for 1 through 8 for tonight. Student practice. You have student practice 1 through 8. You're leaving in just a minute.